We're talking about 11.5 growth and decay. We're looking at this growth and decay with respect to population models. Can we model the population growth or the population decline of many different things? It might be we're talking about a colony of bacteria. We could be talking about the population, the human population of the world, or we could be talking about the wolf population in the western United States. It can come from different scenarios. In whatever case it comes, whatever scenario we're talking about, a common assumption is that population grows at a rate proportional to the size of the population. What that means is if you had a colony of bacteria and that had 1,000 bacteria and you observed that it was growing at 300 bacteria per hour, in calculus we would say dp/dt is 300. The rate of change of the population is 300. We would then expect that if you had double that population, if you had 2,000 bacteria, then you would expect the growth rate to be 600 per hour. So that assumption, that the way we say that is that the growth rate, the rate of change of the population is proportional to the size of the population, is dp/dt, that's the growth rate or rate of change, is going to be some constant times p. So this k is what we call in general the constant of proportionality. Constant of proportionality. And in our case, it's going to be, since we're talking about a population model, it's going to be what we might call the growth rate. And so if k is positive, that means what we're getting is a growth in the population. And if k was negative, then we would get a decay or decline in the population. So we have seen this before, and we can solve this differential equation in general by separating our variables. And you may have done this enough now that you don't actually even have to write this out to know where we're headed. If we integrate both sides, we're going to get to, again, as we have seen several times before, the natural log of the absolute value of p is going to be k times t plus c. And when we exponentiate both sides, that's going to lead us to p is equal to c e to the kt. So many times it will be acceptable even on an AP exam to just skip those in-between steps and go straight from the differential equation to that population growth model of p equals ce to the kt. So let's do an example. We'll say that in our particular case, again, we're starting with this p equals ce to the kt, and we'll say that we are talking about the population of the world, the human population of the world, and after 1950. And so we'll say that the population in 1950, and I'm going to make up these facts here, was 2,560 million. So that's 2.56 billion. And then we know from whatever information we're getting this from that the population in 1960 was 3,040 million. So 3.04 billion. So can we then use that to estimate what we would think the population would be in 2020 right now? So we would, using our population model, we would say times 0, let's call that 1950, to make our life a little bit easier. So that means that our population at time 0 was equal to, and let's say that our P is going to be, we'll measure P in millions to again make our life easier. So that means P of 0 would be 2,560. And then P of 10 would be 3,040. So we had our differential equation, which we knew from earlier, was that dp dt is going to equal k times p. That led to our general solution of p equals ce to the kt. And now using our initial conditions, we can see if we use the first one that the 2,560 will be c e to the 0. And so that means that c is going to be 2,560, which makes our population so far 2,560 e to the kt. We'll use the second initial condition to solve for the k, and so we'll say 3,040 is going to be 2,560 e to the k, and then our value of t is going to be 10. So doing the algebra, we'll divide by the 2560, so we'll get 3,040 over 2,560 is going to be e to the 10k. And hopefully you remember, we're going to take the natural log of both sides. So we'll get the natural log of 3,040 over 2,560. And when we take the natural log of e to the 10k, that's just going to be 10k, because a logarithm-based Euler's number and an exponential-based Euler's number are inverses. And so dividing by 10, we're going to get that k is equal to the natural log. Uh-oh, my pen's not writing very good here. Let me pick a different spot here. Let me go up here. Oh no, I don't think I could have my ink running dry. We're going to get the natural log of 3,040. Good grief. My pen is not writing here. Well, I'm going to leave it to you when we, I can't erase it either. When we do that, the natural log of let me try a different color. If we divide by the 10, oh, here we go. If we divide by the 10, then we're going to get that our k hopefully is going to equal, what did I get, 0.017? And so we can see that the population is growing at 1.7% per year. And the population in 2020, then, we would get that the population, and if we started at 1950 was times 0, 2020 is going to be, I believe, 70. And so we will get our 2,560 e to the at 0.017, and then we'll plug in the 70, and then you can punch that into your calculator to get that population. Okay, I'm going to stop here, and then I'll make another video with a couple more examples.